Okay, so back to some more problem solving. We're going to talk about beat frequencies. And again, so this happens whenever, let me move this around, happens whenever we have two or more waves occurring in the same space at the same time. If the frequencies are separated by some small number, then they will interfere with one another and produce the wah 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 sound. And so the equation for beat frequency, F beat, equals the absolute value of the difference in two frequencies. So this is a unique problem here. We have beat frequencies present if musical notes A and C are played together, which we have these two, and if D and F are played together, which we have these two, and what if all four are played together? So let's kind of talk about that. So for part A, the beat frequency is pretty straightforward. It is the difference in the two frequencies. So I'll start with 264 and 220. So if I play just those two notes, I get a beat frequency of 44 hertz. So it's another frequency, another tone all of its own. In part B, I have two different notes. I have a 352 and a 297. And so that gives me a beat frequency of 55 hertz, which all pretty straightforward and simple. But what if I play all four together at the same time? Now we get a little weird thing going on. I need to think about this because the 352 will produce beat frequencies with 297 and the 264 and the 220. So I'm going to take this and think about this. I have the 352 minus the 297 that I had before. I have the 352 minus the 264, and I have the 352 minus the 220. So those three will give me frequencies that will be, a beat frequency. It will have its own note, if you will. Any frequency that's above 20 hertz, any beat frequency above 20 hertz creates another tone. So remember, sound is any frequency between 20 hertz and 20,000 hertz is a sound. And so if I have a beat frequency that's above 20, it's its own sound. So these are going to make their own sounds. This is going to be 58 hertz. This one is going to be 88 hertz. And this one is going to be 132 hertz. Now, they're all low frequencies, but the collective of that note, this is going to be an F play with D, A, and C all simultaneously, creates an overall sound that are the three notes themselves, plus these additional notes. Then at the same time, the 297 is going to make a note with the 264, and the 297 is going to make a note with the 220. So I get some additional tones coming out because the 297 is also being played. Those are going to give me a 33 and a 77. All right. And then, of course, I have the 264 interacting with the 220, which is going to give me my original 44 hertz. Now, that all seems good and simple, but there's actually more. So these beats are actually occurring and overlapping with one another. And so they actually create some additional ones. So what I have to do now is to get all of them, I have to take this one minus all the rest. And where it creates something new, I have to pay attention to it. It might actually create another one that's the same as something that's already on the list. So I have to pay attention to that list. And I've gone through and done that math. I get additional, if I pay attention to do the math, I'll end up with an additional 74 hertz beat, a 99 hertz beat, I'll get a 30 hertz beat, and a 25. So these four additional appear because of the interaction of all these themselves happening. I know that's kind of weird, but the beat frequency, this is the easy part of the equation, the A and the B, that's straightforward. We expect that. But in the world of music, there are things called chords that are played. When you play multiple notes together, three notes together, you get a chord. Well, that is the three notes original plus the interaction of all their overlapping sounds that creates the overall sound. And so when I play four notes together, I get all of the original four notes, plus I get all these additional sounds coming out that creates a characteristic of the music, which is just kind of weird. Okay, let's go forward a little bit easier now. Let's look at number 16. A piano tuner hears a beat frequency every 2 seconds. Well, what is that? 2 seconds. That's the time between the beats. That's the period of the beat. And if period equals 1 over frequency, then the frequency of the beat is 1 over the period of the beat. So it's 1 over 2 seconds. So it's a half a hertz. So that's the beat frequency. Okay. When listening to a 264 tuning fork and a single piano string, so we've got a tuning fork and a piano string going off together, what are the two possibilities? So if I look at the equation, F beat is the absolute value of F2 minus F1. Let's say that the piano is number 2 and the tuning fork is number 1. So I need to unabsolute value that. So I end up with FB, beat frequency, and I'm going to say plus or minus frequency 1, because if I take out the absolute values, I have to put plus or minus in there. That equals frequency 2. So frequency 2 will be equal to the beat frequency, which is a half hertz, 0.5. We have to do plus F1, and we have to do a half a hertz minus F1, so it's 264. Well, it'd be 264 plus or minus the beat frequency. My fault, I had this backwards. F1 plus or minus frequency beat. So it's going to be negative plus. Okay. My math is going to get weird all of a sudden on me. So I will hear frequencies. The piano, the piano will have a frequency of either 264 plus 1/2, so 264.5 hertz, or 264 minus 1/2, which would be 263.5 hertz. So the piano string could be either of those two, and there's no way to tell which one it is. You'd have to actually, if you tune it tighter, the string frequency of the piano would go up, and then the beat frequency, if it shifted up, we were on the wrong side of it. If it was shifted down, then we were getting closer. Okay. Number 17, I have 2 car horns. One at this frequency, one at this frequency. What's the beat frequency to notice? This is one that you're going to be doing on your own. Okay. All right, the next set of problems is the Doppler effect. So let's go down here. Look at this. What frequency is received by a person watching an oncoming ambulance moving at 110 kilometers per hour and emitting a steady 800 hertz sound from a siren? The speed of sound this day is 345 meters per second. What frequency does she receive after it passes? So the equation for the Doppler effect, let's just start with this. The frequency you hear is the actual frequency of the tuning fork, or of the source of sound, times the speed of sound in air, plus or minus the speed of the observer, divided by the speed of sound in air, minus or plus the speed of the source. Now, I went through all those parameters earlier on another video. So if the observer is moving toward the source of sound, you add. If the observer is moving away, you subtract. If the source is moving toward the observer, you subtract. And if the source is moving away from the observer, you add. So we have some conditions there we have to look at. So in the first picture, the ambulance is moving toward the observer. The observer is assumed to be stationary. So the VO has a 0 value. And so we're going to find out what frequency is received, what frequency is heard by a 110 kilometer per hour. So I got to turn that to meters per second. So 110 kilometers per hour, turn to meters per second. I'm going to take this, so 1,000 meters per kilometer and 3,600 seconds per hour. So if I do that math, I can end up with, this is number 18, yes, with a speed of sound of 30.6 meters per second. Okay, so the F prime is equal to FO. FO is 800 hertz times the speed of sound in air given on this day is 345. And it's going to be plus 0 because the observer is stationary, divided by 345 meters per second. And the source is coming toward the observer in the first part, so it's minus the speed of the source, 30.6. And so if I do this, 345 divided by 345 minus 30.6, all times 800, I end up with a sound of 876 hertz, which is reasonable in that as the sound is coming toward the observer, the frequency shifts up. So it was 800, but it sounds like it's 876. Now some time has passed and the ambulance has passed the person. Now the ambulance is going away. So we're going to change our parameter here from a negative to a plus. And so as it's going away, F prime is 800 hertz times the 345 meters per second divided by 345 meters per second. That's the speed of sound in air. And it's going to be this time plus 30.6. And so our frequency that you hear as the ambulance is going away has now switched to 735 hertz. please note the effect, even though the speeds are the same, 30.6 in both cases, the effect of going away or coming toward, we have a 76 hertz positive shift. Going away, we have a 65 hertz negative shift. It reduces it by 65 hertz. They're not equivalent numerically because adding and subtracting does change the value of the denominator. Okay, number 19, using just this idea, I want you to do number 19. That's one that's assigned to you. And you're going to look at this. Look at a mouse that is sitting still. So the mouse is observing. We have a hawk flying in at a 25 meters per second and screeching at a frequency of. So if the speed of sound is 331, you're going to find it. Now the observer is stationary and the source is moving toward. So if I look at that option above, just like number 18, the observer was stationary and the source moving toward, that was this one. So we're going to use that form of the equation to solve for number 18. Number 20 is a little bit different in its approach, so I'm going to do that one with you. A commuter train blows its 200 hertz horn as it approaches a crossing. The speed of sound is 335. An observer waiting at the crossing receives a frequency of, so that's what they hear. What is the speed of the train? So we're going to take this equation and solve for the speed. So F prime equals FO times the speed of sound in air. So the observer is stationary, so it's plus 0. It's going to be a plus 0 there, divided by the speed minus the speed of the source because it's coming toward them. Okay. And so we're going to just impart A. So we're going to solve this for VS. So step one is to, I would probably say, let's multiply through by the denominator. And so we end up with V minus VS times F prime equals FO times V. Now I'm going to divide through by F prime. So V minus VS equals FO over F prime times V. Now I'm going to, at this point, all I have to do now at this point is actually do a little subtraction, a little math. So if I want to switch, I'm going to multiply this by -1. It's okay. I'm just going to rearrange this. So the speed of the source of sound is equal to, in that case, it's going to be V minus FO over F prime times V. And so the speed of the source of sound is equal to V times the quantity 1 minus the ratio of frequencies as it's coming, as the source is coming towards. So right off the screen there. So that's my working equation. And so the speed of the source of sound will be that information. And so the speed of the source of sound is equal to the speed in air, 335 meters per second, times the quantity 1 minus the frequency of the observer, 208. No, frequency original, excuse me, 200. That's FO. F prime is the frequency of the observer here, divided by 208. And so 335 times 1 minus 200 over 208. That's actually a pretty good fraction. It's close to 1. Hopefully the train's not going close to the speed of sound. If I do the math and figure it out, I can see that the train is moving at 12.9 meters per second. Okay. And then it says in part B, what is the frequency as the train moves away? So now we're going to take the equation F prime equals FO times V. The observer is still stationary, and the train, the source, is now moving away. So I'm going to add V source. At the bottom, I have V source here. I just found it. So the frequency that they will hear will be the 200 hertz times the V. V is 335. Divide by 335 plus, it's a plus 12.9. So the frequency they hear in that case will be 193 hertz. Okay. I think I'm going to let you guys do those on this page. So 21. I'll look at this with you for a minute. A tube filled with water has a valve at the bottom. Water flows out as the water is being emptied. So this is like the lab we did. The length of the air column changes. A 1024 hertz tuning fork is placed at the opening of the air tube. So we're going to start out. The tube is full of water all the way up. and the water level begins to drain down. And so the question is, when we get to this L, it will resonate, and then it'll resonate somewhere else. I'll call it L1, L2, and it'll resonate somewhere else, L3. And the question is, what water is removed from the tube until the n equals 5 mode of the sound wave. So n equals 5. What is the L when n equals 5? And so this is a closed tube. I'll give you a little hint there. And you got the speed of sound in air to be found from the temperature of 18 degrees Celsius. Okay, let's look at number 22, also on your list to do. A flute plays a note with a frequency of 600 hertz. The flute can be modeled as a pipe open at both ends, where a flute player changes the length of the finger with his finger position. So as they use the buttons on the flute, they're changing the length. What is the length of the tube if this is the fundamental frequency? So this is F-O, and it's open at both ends. So again, it's a tube. And then number 23 is a problem. It's a string, has a linear density and a length and a tension, and oscillates at n equals 3. That means it has 3 loops. If you think about it, it looks like this. I can't draw it very well, but there we go. That's n equals 3. It's what it looks like, where the length is equal to 3/2 of a wavelength, in case you need to know that. Okay. What is the frequency of the oscillation? So you're trying to find the F of this when it resonates at n equals 3. So n equals 3. That's important to note. Find the change in the frequency when the tension is increased by 10%. So you're going to use the Fn equals nv over 2L. I'll just rewrite it, Fn equals nv over 2L, because it's a string, and you're going to use V as the square root of the force of tension divided by the linear density. You're going to use that information as well. So again, these 3 problems are on you to do. We will address those at a later time. And this makes this the last video.